Physics students of electricity, of static electricity, let's talk about Gauss's law as a way to investigate a couple of nested conducting spheres. This is a sphere here, a solid conductor with a net charge positive 2q, and this is a thick conducting metal, well, conducting shell that surrounds, these are both spheres. All right, so we got a cross-sectional look here. And this one is concentric with the one inside it. The shell and the inner sphere are concentric. Now, this outer conductor has a net charge, negative 8q. All right, the question is, what charge exists where specifically? All right, and here's the deal. Well, one thing we have to be okay with is we have to be okay with the fact that this system is in what's called electrostatic equilibrium. And that means that charges have moved to a position where there is no more force acting on them, and they don't move anymore. All right, and they don't move anymore, again, because there's no force acting on them. There's no force acting on these charges because there's no field in the area in which they reside. So that's a way of saying that the electric field inside a conductor is zero. It's a big deal. All right? And again, we say that because if a conductor has reached electrostatic equilibrium, it means that charges aren't being pushed around anymore. They're not being pushed around anymore because there's no electric field. Because electric field is what exerts electrostatic force on free charge. So that means that inside this conductor, E equals 0. Oh, let's define the following. This inner conductor has radius r. This outer conductor has an inner radius 2r and an outer radius 3r. Okay, so the deal here is we can definitively say that the field everywhere inside this inner sphere is 0, and that the charge all exists on the surface. Now, we can justify the fact that the charge all exists on the surface here is positive 2q on the surface of that inner conductor, because Gauss's law says that if there is a Gaussian surface, that's my green circle, really sphere there, if there is a surface and across that surface everywhere there is no field, it must mean that that area encloses no charge. Gauss's law says that the surface integral of electric field vector and every little dA vector, that dot product is Q enclosed over epsilon naught. All right, and the only way, because these are dAs of my Gaussian surface. My Gaussian surface is this green sphere in here, and well, the only way the integral dA there is not 0. The only way for E to be 0 is if that surface encloses 0 charge. All right, so there's no charge inside that. There's no net charge, I should say, on the inside, on the interior of that sphere. All net charge exists on the surface. So this surface, the outer surface of the inner sphere, contains charge positive 2q. Now, the outer sphere, the outer spherical shell. Remember, the field inside that conductor, and I mean E in here, is 0. And that's because this outer sphere, outer shell, is in electrostatic equilibrium. Charges have moved, and well, they stop moving. They stop moving because they're not being pushed anymore. They're not being pushed anymore because there's no field. There's no field in there. And that means we can use that fact to say, what if I look at this Gaussian surface? That Gaussian surface exists in a place where there is no electric field, or in a region where across the surface there's no electric field. And that means that that surface must enclose no charge. And what that means is, since there is charge positive 2q on this outer surface of the inner conductor, there must be an equal and opposite charge negative 2q there. All right, because for this Gaussian surface, if E equals 0, then Q enclosed must equal 0. Same thing here. Now, this outer conductor has a net charge of negative 8q, so that means that across or on this outer surface, negative 2q of the charge is on the inner surface. The outer surface contains charge negative 6q. You dig? I dig. Now, we also want to be able to plot, not that, don't look at that, plot the electric field as a function of r. All right, and so let's look at a couple different areas in field, I'll say. Let's look at a couple different areas. Well, we know that at a location where we are inside radius r, we know that electric field is 0. All right, so let's look at a region between the outer surface of the inner sphere and the inner surface of the outer sphere. So we're looking here. Here is a Gaussian surface of radius r. All right, Gauss's law says surface integral E dot dA is Q enclosed over epsilon naught. Now, we have chosen a Gaussian surface that is a sphere. All right, and because symmetry arguments say a couple of things. They say that everywhere on this surface, this black surface that I've chosen in here, a couple of things, now it's green, sorry. Everywhere in there on that surface, a couple of things are true. One of them is that E from this inner sphere is going to point outwards, right? And all the dAs from that inner surface from this Gaussian surface point outwards. What I'd like to do, so what we have, so this is really like saying here's a field from that inner conductor and here's my Gaussian surface. Well, the surface has dA vectors that look like this and 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 so on and so on, because the area vector, or really the dA vector, has a little dA and by definition points in the n hat direction. N hat means normal. Normal means perpendicular to. Okay, so by definition, dAs point out, perpendicularly out from any surface. All right, so the big deal is E and dA everywhere are parallel. And that means we can, if we're being super judicious here, turn this into the scalar product of these. Because we're really saying, well, vector magnitude E times magnitude dA times the cosine of 0, and the cosine of 0 is 1. All right, so that's Q enclosed. So I'm going to start right now by saying that's 2Q over epsilon naught. Now, everywhere on our surface, symmetry arguments say that E is constant, because our Gaussian surface has been chosen to be equidistant from the center of that inner sphere. So we can take E out of our integral and integrate only dA to epsilon naught. The surface integral dA is, well, the sum of all the little dA vectors, which is the area of that sphere. So this is EA of our Gaussian sphere, or E is plus 2Q over 4 pi r squared epsilon naught. Now the 4 pi epsilon naught, or the 1 over 4 pi epsilon naught, that's K. Right? So this is okay to write as positive 2K Q over r squared. And yeah, that agrees with a very basic form of Coulomb's law that says if you have a charge and you're some distance r from it, then the field strength here, if this is positive, is KQ over r squared. That says KQ. Here's a charge Q. Well, we happen to be away from a charge 2q, so hence this positive 2kq. Okay? Now, a couple of values of that are important. So that's in a general region between, in this general region in here. See where I am? In this region. All right. A special place we could say, well, how about at r is big R, at the actual surface of that inside one, we get that E is 2kq over big R. Let's do the same thing, or take a similar approach, but now say, now we know, right, that if R between 2R and 3R, we're inside that outer conductor there, E equals 0. So now let's look at for R is bigger than 3R. Well, this stuff sort of remains so we're going to use Gauss's law. We sort of get here, except not quite that. We're going to get all the way, I'm going to get down to, let's say here, because we don't have to be as judicious, I don't think, again, with why this is equivalent to that, as equivalent to that, as equivalent to that. But what we can say now is E times A is Q enclosed. Well, inside this Gaussian surface of a new radius R, outside of 3R, our Q enclosed is both of those charges, is negative 6Q over epsilon naught. Or E is negative 6Q over 4 pi, watch this, instead of 4 pi r squared epsilon naught, 4 pi epsilon naught r squared. So this is negative 6 kq over r squared. All right, at an important place, let me move this over here. An important place, we can say at the actual surface, at r is 3r, at that very outer surface, this E is going to be negative 6 kq over, that's 3r quantity squared, 9r squared. So that's negative 2/3 kq over big R squared. And look, here's a kq over, whoops, big R squared. Now we have another, well, we can compare those electric fields pretty precisely. All right, so watch this. Here's a plot of E as a function of R. All right, and I'm going to say there are some important places, like here's radius R, and there's 2R, and there's 3R. That allows us to say what's out past that. And remember, what we had was the biggest the field, the biggest the field gets is this, positive 2kq over r squared. And then we also need this one on there, negative 2/3. All right, so how about this? We'll go like, there's 1 and there's 2. This is positive 2 kq over big R squared. Everywhere inside the inner conductor field is 0. Then we jump up to here. Now, in this region, the field is 2kq over r squared. We look at this, we get this inverse square dependence of field strength on r. So look, r goes from, in that region, from r to 2r. R doubles. E must get 1/4 as big, so it says inverse square relationship. So we go from 2kq down to a half of kq over r squared. And here's our data point there. And this looks, okay, something like that. Pretty not bad for an inverse square, fine. Okay, then we said field drops to 0 inside that conducting shell. And then outside, Remember, we had at the surface radius 3r, we had that the field was negative 2/3. So here's positive 1, here's negative 1, here's 2/3, right? Yeah, sure. So this looks like, say, here, and then does some inverse square-y stuff like that. And if you want, you can say these are called discontinuities. Here's one, here's one, here's one. At the surface of every conductor, there exists a discontinuity in electric field. And that's because, by definition, inside any conductor, the field is 0. And outside any conductor, if the conductor is charged, there will be an electric field. So there has to be a field that goes from 0 inside to something outside, and thus we get what's called that discontinuity. It can be shown that at every whatever you want to call it, interface or surface, really, there is a discontinuity that depends only on one thing, and that is charge density. That discontinuity must be the charge density at radius r over epsilon naught. This discontinuity must be the charge density at radius 2r over epsilon naught, and thus, or not and thus, but as follows, at 3r over epsilon naught. And I'll show you, without doing some actual calculations, I encourage you to actually calculate what this is, and you're going to, guess what, you're going to get this number, because that's how tall this is. The discontinuity is the magnitude of that difference. Well, this is 0, and that's 2kq over r squared, so that discontinuity is equal to 2kq over r squared. You should be able to show, you should go to some lengths to show that sigma over epsilon naught is indeed 2kq over r squared. But what I will show you is this. If we look at these two, talk about a mess of a diagram. If we look at two of the surfaces, in particular this one and this one, and this has a surface charge plus 2q, and this has a surface charge negative 2q, and this has a radius r, and this has a radius 2r. Well, this surface area is, let's call it A, 4 pi r squared by definition, right? This surface area is 4 pi r squared, but r is 2r, so this is a surface area that's 4 times as big, right? Same charge, 4 times as much area, which means that, remember, epsilon naught is epsilon naught. This charge density is charge per unit area. This charge density is charge per unit area. This charge density is 2q over A. This charge density is 2q over 4A. The charge density is 1/4 as big. And thus, this discontinuity is 1/4 as big as that. An inverse square says that that's a certain field strength at twice the distance from the center. The field strength is 1/4 as much, so those things jive. And you can show the same thing here. I'll just do it. I'll just say it. There's 3 times the charge out here. The sign doesn't matter. 3 times the charge at 9 times the surface area. That's a, what do you call it, a charge density of 1/3 as much as here. And look, this is 2kq over r squared. This is 2/3, 2 over 3 kq over. So that still works. That these discontinuities only have to do with the charge density of the surface. And in particular, the continuity is equivalent to charge density divided by epsilon naught. Not bad, right? I say. All right, people. Um, to recap here, the important thing you have to be able to apply here is that for a region inside a conductor, the electric field is zero. All right, and we can then use Gauss's law to say, okay, well, if I know that electric field is zero there, I'm going to decide to put a Gaussian surface there. And that means that everywhere or within that surface, the total charge must be zero. And then I can talk about if I know a charge on one surface, that tells me the charge somewhere else. And then addition tells you the rest of the charge. That's this great little exercise. All right, the exercise of then using Gauss's law to write expressions for electric field is also certainly a valuable one, and we should be able to make very graphically accurate plots of those fields if we're willing to be a little careful and be provided with some friendly numbers. All right, adios.